using this space, starting with Hadoop by means of Cloudera. And we deliver our services using bare metal machines as opposed to virtual machines. And these bare metal machines have 4 10G connections. They have locally attached drives, but at the same time we can deliver them in about 2 minutes. So if you want to have a cluster of 10 machines, physical machines with drives and everything, you can have them in 10 minutes. You can release them after another 10. Well, in 2 minutes and release them after 2 minutes. So it's a very flexible way. It's purely on-demand model, just like you find in AWS, but it's designed for big data workloads. It uses bare metal. This is important, and because you get a lot of performance from bare metal machines when it comes to high memory footprint applications. We also have a very nice software-defined network. We can automate a whole bunch of switches, essentially connecting any 2 ports of the network in a layer 2 broadcast domain. So you can have layer 2 within your network and the machines. And so it's very, very fast, very low latency, high throughput, and SSD based in terms of the storage fabric, which is distributed storage fabric, and a lot of other stuff. So I'm on board with this. If you like, I can talk more about what we do and how we do later on. Okay, so my idea or the basis of this presentation is the fact that we've been, or at least I've been, somewhere at the border between big data technologies and the general purpose architectures and general purpose infrastructures for a while. I've been doing general purpose hosting and seen a lot of architectures as well as big data hosting for a while, and big data related architectures and big data projects. And I think that there are a lot of parallels and a lot of stuff that can be learned by drawing conclusions, by moving concepts and technologies from the big data field to the mainstream and vice versa. And this particular talk is about moving some of the mainstream technologies into big data, things like Docker and microservices in terms of architecture and approach, and bringing them into the big data field. And some of them are just my inner ramblings, so I'm not telling you how you should do things, but rather what it's out there, and you should make your own decisions. And Docker and Mesos are seen increasingly in the wild, and I know Mesos works with Spark, but I'm not necessarily going to talk about that. I'm going to talk about something else, and you'll see. Okay, so the concept of a data lake per se, right, starts from the idea that data is, as we all know, something that can get more important after a while when we have the proper tools and the proper time to analyze it, right? And as we can get a CT scan on a mummy right now, something that the British guy couldn't do. Now it's gotten a lot easier to get more information from the same data and from the same artifacts that we have discovered previously, simply because we have a new technology and a new approach, and probably we look for different things. So the idea is that you might want to hold on to your data, even though you might not have a use for it now. Now, this does not necessarily mean just stockpiling it. So as I said, the data lake itself is more of a concept than a technology. So it's not a software that you can label, well, this is my data lake and you can do something with it, even though, by the way, we have a data lake product. But I'm not talking about that. The data lake is a concept. So the concept just says that a lot of value comes from correlating information, right? From correlating different data sources, correlating social media with something that you have in your ordering system. And at the border between these data sets, there's a lot of information that can be extracted. Now, technology itself has posed some challenges in this thing, because you have, in order to be able to store machine data alongside structured data, something like a SQL, like a relational database, you traditionally had to kind of fit a square cube into a round hole by normalizing information, trying to fit it into a database, not necessarily built for that. So the concept now is you want to keep the data as it is alongside structured one. Now, again, I'm not referring necessarily to storing it within the same system. It can be different systems, but the idea is that you want this data to be available at the same time to the data scientist, that he might be able, or she might be able to actually get some more information out of it. And traditionally, in big organizations, you had silos. Right? You had Department X and Department Y had his or her databases, and even though the information existed, it was pretty hard to get the networking, at least, to cooperate and be able to extract data from there. And so we're trying to address this problem by having a strategy of bringing data at the same time. Okay, bear with me, it's going to get more interesting. And if about microservices, what I'm kind of introducing is the concept of a data service. Right? In my view, on a data lake, is that it is a collection of data services rather than just a place where you put data into. And there are a lot of paradoxes in between microservice and the concept and the data service, and you will see exactly what I'm talking about. And the screenshot that we have there is from a project that we did as a proof of concept for one of the UK's largest same-day parcel delivery service. Essentially, they have people taking package A, moving it from point A to point B. And what we did for them was we had a whole month worth of data about the guys' movements and where they got the package and where they delivered. And the objective was to optimize the business, of course, and see what we can come up with. And what we did was we did a little bit of clustering, so we can see where the focal points of the delivery mechanism is and where people have more packages to send from, as well as the routes of those delivery men. And the idea was that I want to be able to predict with a certain probability where should I, if I'm a guy that picks up packages, where should I stand and where should I leave from that point towards my destination? Because if I know that at one point I'm going to get another package, right, I might as well stay for another hour, get the new package, and then essentially cut my costs in half because I'm delivering the package over. They asked for a timetable, right, for when should I leave or should I stay if I'm a carrier. And also, what we identified is that we can tell the guys which route to take in order to optimize. So it essentially increase the chances that I can pick up a package from somewhere on route, right? So instead of going on on the highway, on an M5 highway, I can just bypass it a little bit, and because chances are I'm going to pick up something on the way. So I'm hugely optimizing the business this way if I have these information. And long story short, these steps that I've been describing can be reduced to a collection of data services that I could have actually built for this company. So this company has a cluster service that provides clustering information about clusters of packages on that particular data set. Now there's another, and that data service is being consumed, that the cluster information, just the geospatial information of those cluster centers and the size of them can be offered as a service to another data service that could use them to create the timetables, right? And so forth. And so right now, for this particular example, I have the timetable, the driver's path optimizer, and the service center load predictor. And they all use data from each other, right? The data itself can reside into the same HDFS. I'm just talking about who has the responsibility of building that algorithm, right, and evolving it over time. And actually, the problem is not necessarily the technology side of it, but rather the team that are behind this making it happen. And you'll see, and we'll talk a bit about microservices as a paradigm, or as a concept. and see where this comes from. And this does not happen yet in big data because there aren't as many data scientists working on the same data yet, but I'm pretty sure there are going to be a lot more data scientists working on the same data sets, and so we will hit these problems sooner or later. So let me tell you what happens in the general purpose programming field. So have you used any MVC, model view controller models so far in creating web applications? Or great. So you kind of know that you essentially split people in your development team into 3 categories, more or less. UI guys, backend guys, and DB guys. Right? Some of them, DB and backend, are kind of blurred, but at least you have some folks knowing more DB than others. So then you have this typical side. And the problem with this has worked properly, more or less, until now. The problem is that with this ultra specialization, you usually, when you create an application, you first try to model the application, you model the data, and you model the way your objects look like, and that's where the DB comes from, right? And then you start essentially implementing something around the backend services, and probably somewhere over there you start working on the UI. And this sequence of events takes not necessarily a long time, but a fairly long amount of time, something like at least a couple of months or a few months. And then you reduce this down over time by maintaining everything for maybe 1 month of release cycle, and you create this monolith, this application that has all of these components, and you roll them out at the same time. And the problem is you have to wait until all the components get into place before rolling out the application. You have to do QA, and you have to do proper unit testing. But mostly it's QA, because there are so many moving parts from so many people that you want to make sure that they fit together before you release them. So that's why it takes a long time. And a month is a very optimistic thing. Agile has kind of solved this and tries to solve this problem, but you know about its pitfalls. So this guy Conway postulated that, or observed that, organizations tend to mimic the organization architecture in the application architecture. So it essentially, you see well-written APIs between teams that communicate properly with each other, and poorly written APIs and poorly written communication in design where teams don't really talk to each other properly. So you have a very good connection between backend and backend, because they essentially call functions from one another, and you have abstractions and interfaces, right? But sometimes the UI guys don't really get it, what happens in the back, and at least it takes a longer time to do stuff. Anyway, now an alternative to this, and by the way, this is why microservices appeared. It's not a technology-driven driving this forward. It's rather the required change in organization. And the concept is that if you take everything that an application is built from, right, all the components of that application, and you split it into functional components, things like, think about a shopping cart, right? A shopping cart could be a component in itself. And then you would have a backend service, right, that processes orders, like an ordering processing service, and then a provisioning service, right? The shopping cart could be a component. It could be developed from A to from top to bottom by a single team that knows UI, knows backend, knows DB, and has a responsibility for rolling that piece out. Right? This is how a lot of the huge Amazon scale or Netflix scale companies do it. But this poses by itself a lot of technical challenges, because if you can't just write a module and then release it, right? Because it's part of a big thing. You have to do QA, and you have to make sure that it works with all the other modules, and you end up in the same place. So the problem is twofold. So one of it's an organization problem, and the other is a technical problem, and you need both to make this work. But ideally, if you could roll out just the shopping cart or just the backend whenever you want, and just push it there with on your own schedule, just the two of you or the three of you, or how many guys you are in that particular component, that would be ideal, because then you have all these independent release cycles, and you can evolve a lot faster. You know what I'm talking about. The smaller a team it is, the faster you can do, can get things done. And the concept of microservice essentially is this. You have to have smaller teams developing smaller components that have independent release cycles and independent development systems. Now, again, the monolith versus microservices, you have the application servers. The way you scale things now is essentially you have all the components talking to each other directly by calling APIs, not APIs, but rather function calls, right? And residing within an application server. And if you want to scale out because you don't have enough capacity, then you simply copy that monolith over and create another application server and you load balance across them, right? And this is fine and then it works, but suffers from the other longer release cycles that I've been telling you about. Whereas in microservices, of course, because microservices themselves are very small, they occupy the same space on the same servers, but rather in a more distributed and independent fashion. And I know this is very high level, and we will get into more details about how this is done. And oh my god, I have so little time. Okay, Polygon persistence. The concept is that if you have microservices, and these services are developed by a particular team that has a particular preference in using maybe Couchbase or maybe Cassandra or maybe whatever storage mechanism, then by all means let it have it because it's part of the architecture. And so the difference is between having all these components talking to a single database, be it Oracle or anything that scales somewhat, versus having a multitude of technologies for storing things. Right? So this is the way you usually do it in microservices, and also very important in microservices, you want to be able to scale each of these layers independently from each other. So the shopping cart should be able to scale, and then it should have like a queue to dump the orders into, and then the backend services that actually provision what the guy has ordered should scale as well, depending on how much time it takes to actually provision the service that the guy has bought, depending on the time of day and the time of year. And so you kind of need different technology, different tools for different things, and the polyglot persistence comes from this concept of having different tools. There's also polyglot programming paradigm, which says that you might have different programming languages in your microservices. It's not bad; it's good because a web-centric approach might have too many. You need to change things really, really fast. So you need something like maybe PHP or Python or something that's easier to write into and change, whereas some backend service might need Java proper, and some data-intensive tool might have Scala, or I don't know. It depends on your preference. So these are like the general principles of microservices architectures. You need components rather than layers, although they could be layers, but they're not one on top of the other. They're like a cloud of things that work together. You want to be able to expand every container. And you want to, it's a very important thing, you want to be able to be backwards compatible. So if I'm rolling out a new container, right, with a new version, and because I don't know about all the other components, I want to make sure that I want to, at one point I want to be able to talk with another version of another container. Right? So I want to be able to survive these different versions of the containers, to the point where I have my own container having multiple versions at the same time. So maybe I want to do like a rolling restart, right, of a service. So there's a lot to be said about this, especially around coordination within all these services. But it's not like an operations talk, and we still have a lot more to go. Docker. Who has used Docker before? So for those of you who haven't used Docker, Docker is not a VM and neither a VPS. It is essentially a way of, and actually I'm referring to the Linux containers part, which is used by Docker, is just a way of isolating a particular process so that it looks like it's running by itself within the kernel. The kernel is the same for all the processes, just the processes are isolated. And if you have this together with a way of limiting the amount of resources that the process consumes, as well as a way of having like an independent virtual network card for every, let's call it, container, you have like a namespace where you can have a little operating system, but every operating system runs within the same kernel. So the same kernel space processes think they are inside they are alone, but they are essentially in the same kernel space. And the good thing about this is that there's no overhead because of having to replicate the operating system over and over again. So you don't rerun the kernel for every single time. So this brings a lot of performance increases on bare metal. So it's very easy to use. And because there's low overhead, it makes sense to have like hundreds of them on a physical machine. We'll get into more details later on. And Docker, by the way, Docker just comes with the capability of rolling out an image. A Docker image is the files that that particular process sees when it runs, right? So it's just, there is a concept of chroot, change root in Linux. You could always do this essentially, but Docker brings it to a new level. It uses Git-like repositories for images, and an image is just a collection of files. Let's say CentOS is a collection of files, and if you want to install something on a container, you clone the CentOS, you install something, maybe HTTPD or Spark on that container, and just keep the differences between. It would be like a branch, and you store the differences, and you upload the differences into a Git repository or a Git-like repository, and whenever you instantiate a Docker container, you pull that image, CentOS image in your branch, and you instantiate it. You create a process within that container. Right. The containers themselves are usually designed to be stateless. This means that whenever they disappear, all the data disappears. Actually, it's not necessarily true. The data is still there on the file system, but you have to make it work, to make it persistent. You have to do some mapping between the host operating system, the host file system, and the container file system, unless you are truly stateless. And the point is, you want to be truly stateless at the container level. You want to have your state stored in another technology, something like maybe a database, something like Couchbase. And Couchbase, you'll see, is a lot faster than a lot of things, especially file systems. But just in case you want to do persistency with Docker, you can do it this way. Docker networking, and this is very, very interesting and very complicated, especially if you do Docker networking across multiple hosts. So Docker networking within a single host, because Docker just knows about a single host, at least right now. Doing it across multiple hosts is problematic, and this is where Mesos and Marathon comes into play, and Bigstep, by the way. We essentially are able to automate Docker across multiple hosts. Right? So what we can do now is we can issue an API call and create a container or a bunch of containers that together make up an application. Right? And these applications are this collection of containers are connected between each other using a layer 2 broadcast domain. And every container has an IP, private IP, and it just resides there. Now the problem with this is that let's say you have a service running within a container, something that listens on port 80, and anything that listens on port 80. You want to be able to get the customer to get to that container, right? And to do that, there are a certain level of load balancing that happen automatically and out of the box in this environment. First of all, so the container listens on port 80. This port 80 gets mapped to a host level port from the range 32,000 and something. And then HA proxy, if you used before, which is a load balancer, gets to listen to what's called a service port. So every application has a concept of a service port and a container level port, right? And you just tell Marathon, hey, I want you to listen on port 80 for all my containers, that each of them listens to port 80 or 8080 or whatever it is. And then HA proxy does the load balancing across all the containers in this host. And also, by the way, all the other hosts. And so you have, and at the same time, this is the public IP, right? So the HA proxy listens on the public IP. Every host has a different host name, but they all can share the same host name. And there's something which is called a DNS load balancing, and whenever the browser asks for the IP of that particular DNS entry, it gets all the 3 IPs of all the hosts. And every host can then redirect to all the other containers that listen on that port. So long story short, you get complete load balancing out of the box, right, across all your hosts. So whenever a request comes, it gets redirected to one of the containers. And you can have as many containers as you like, and you can have as many hosts as you like. And the most interesting thing is, any host can fail at any time. You still have enough, you still have containers, and you still have a way for customers to get there. And you can create any number of containers in this environment, and as I said, a number of hosts. It's very, very cool because you get failover out of the box, besides capacity increase. So it manages, you essentially create applications against something which people call a distributed operating system. And I will talk a bit more later on. Okay, now performance. This is a test that I've done with Cassandra a while ago. What's important here is these three things. So very close to each other, these are milliseconds in terms of response. So running something within a container is really fast. Of course, if you stick multiple containers to the same host, you get a degradation in performance, but that's to be expected. So again, so this was for latency. So latency is pretty much the same. This is for throughput. Again, about the same. So you don't get a degradation in performance. There is one, so it's not completely zero overhead, but the overhead is very, very small. A lot smaller than virtualized based application. Right, so I've told you about Mesos and Marathon. Again, they orchestrate applications, and an application is a collection of Docker containers that are being supervised, so whenever a container dies, it gets respawned on another host. Marathon also manages the HA proxy configuration, so whenever you spawn a new container, you allocate a new host IP or a host port to it. HA proxy configuration is updated, so you don't touch that part at all. So it helps you create applications really, really fast, and they spawn instantly. So it's very easy to create a highly available and high performance application using these tools. Now, streaming. Who has used Spark streaming or uses Spark streaming in production? I'm not, but maybe you are. Okay, just wonder. So if you do streaming, by the way, streaming has a different resource utilization pattern than the normal big data workloads, in the sense that, typically you get a resource utilization pattern like this. You use 100% of the resources available until you finish your job, and then you stop. And then you start with, a little bit, and you do the same thing. Whereas with streaming, it's more like the traditional, like web-based applications, and you have like this seasonal workload, and you never truly get 100%, but you need to have some resources available for the spikes. And this is where, in order to be hugely effective, you want to have higher consolidation ratios. So you want to have multiple containers running on the same box to make sense. At the same time, you want to be able to scale up. So this is, again, why, at least for the streaming part, you should consider building something with Docker. And Spark with Mesos, Spark can directly use Mesos, not necessarily through Docker. So you can reuse the same Mesos cluster for Spark as well. But if you have Kerberized environments, you should use Yarn. And Yarn plus Mesos, because Yarn can run in Mesos, so they're not necessarily fighting each other, because Mesos is very fast in spawning processes as opposed to Yarn, but knows absolutely nothing about the environment where the application resides, so has no capability of authorizing itself towards a Kerberos server. So there's a project called Myriad where you essentially run Yarn within Mesos in order to be able to do that. So if you want to use Spark with Mesos, you can, as long as you don't have Kerberized environments. Now, so coming back to what I wanted to tell you initially. So I'm creating a data lake, right? So the data lake, if I now have this technology called Mesos and Marathon and Docker and everything else, I can create what I call a data service. Right, so every data service could essentially be something like a Spark streaming, or it could be a collection of little batch services that periodically get the data and transform it, or it could be anything that you can think of that transforms the data to a certain degree and makes it available essentially to the rest of the organization. Right, so I have the data team here and the data team there, and they can talk to each other. They can use the data that the other team has provided. So think about I like to think about the data lakes in terms of making a data ecosystem, if you like, within my organization. So I want to make kind of open source the data that I'm producing, and every time a data scientist writes a really clever algorithm that extracts what's important from a particular set of data, that data might very well be very important from some other guy, some other data scientist trying to do its own calculation. So we're not just working on the raw data, right? Everybody working on the same raw data, but rather working on the data that gets created out of that. So this is not necessarily big data. This is more like a tree-like structure. So I'm building on what other people have built. But in order to do that, I want to make sure that all these data services are scalable enough that I can service all the other guys, right? That can be changed. Because if one of these services starts to being used by another guy, another team, another department perhaps, then I don't want to break their jobs because I've changed the output of my Avro format. So you want to make sure that whenever you create a data service, you want to create it in a way that it gets evolved, right? And there are technologies to do that. For instance, with Kafka, and I think the best practice nowadays is to use Avro within Kafka to be able to evolve the schema over time. And there's such a thing called a schema repository or a schema service that you deliver by Kafka that can tell you each component or each data service what is the version where consumer X is at this point. Like I know that if I have a consumer that is at older version and I want to include some additional information, so I can take these kind of decisions to make sure that my environment stays stable and I can service all my other colleagues and components. And so I think this is what a data lake is. And I think that this collection of data services does not necessarily mean keeping all the data in HDFS or keeping all the data in Cassandra or Couchbase. It just means that I want to make sure that everything that I do is for the benefit of the organization and that everybody has access to this data, but there are multiple levels of it, right? And there are tools to help you with that. It is important to use the concept of a microservice as well as perhaps the technologies behind it, things like Docker or just Mesos by itself as a multi-purpose architecture. I think Mepar calls this Z architecture. And it's essentially reusing the same resources in different ways depending on the situation. And because we come up with a lot of new technologies very, very fast. You see the big data domain evolving really, really fast. So you have all these, I have the data stored, let's say, in HDFS, but then I want to make sure that I want to spawn a new IPython or Jupyter notebook. I want to use it to look at the data, or maybe Sparking to do something else in emLib, a new cool machine learning algorithm, some neural net implementation that I want to try on my data. So I want to be able to experiment a lot easier than what we can do right now. So I want to be able to spawn new processes and rip them off just as well. So this is why it is better to have stateless services as much as possible, so I can destroy the containers. And the state that I'm talking about resides on additional services and things like Zookeeper, things like Kafka, but you know all about that. So as I said, it is more a concept than a set of technologies. And I think we actually have the technologies to make this work in this way. Oh yeah, and survey discovery is very important. Because if you have a whole bunch of, and I've seen a lot of people talking about it actually, because once you have a whole bunch of data services and you have a gazillion tables with structures and fields and everything, it starts to get messy. No single guy knows about what that particular data means. So that's gonna, I think, is gonna be one of the the next biggest challenges. How do you make sense of all the data that you have? Where's the kind of like a glossary of what all that thing would mean? And I've seen applications doing that, kind of a data inventory, if you like. So there are ways of doing it, but still, I think we're in the early days of this, and we'll see some other solutions on this field. But I would really like to have this kind of environment in my organization. Yeah, so this is the end. I've been moving very, very fast. As I said, I have like a hard stop, but there's another 15 minutes for questions or ramblings of your own if you have opinions and would like to share them. But let's start with the questions. Anyone? No questions? Do you think it's a good idea or not? Who is for it's a good idea or nobody's for a good idea? Who is for it's a bad idea or not very good idea? So you haven't made up your mind yet. It's okay. It's okay. Yeah.
Talking about data lakes, how different actually it's from data warehouse?
So as I said, it's not a technology, right? So it's a collection of services, of data services, and the concept of actually bringing all that data in an accessible manner for everybody that wants to use it, rather than having a data warehouse. But the main difference between a data warehouse and this is the fact that you have structured data and unstructured data side by side. That would be like the textbook answer for that. And unstructured, when I say unstructured data, I mean things like articles. Right? And it's harder to fit. I mean, you can put an article in a database, it's not a problem. But maybe you want to index it in some other way, like an Elasticsearch index, so you can do like stemming search on it.
But I would say in this case that's more like data marts. So if you want to bring something useful through any department, and then someone else realizes that it is useful for me as well,
I suppose.
I would say yes. Data mart can solve this. So because it's pretty much, first of all, it uses something what people thought about, that this piece of data can be useful for a company, for department, for any group. So it was already some effort made to make it clear that we will use this. So,
but how many organizations have a data mart?
That's a question. Why we should replace existing thing?
I don't know. What I'm asking is how many do actually have this?
We use.
Okay, and how do you do it?
So that's of course based on requirements from any kind of department which says, okay, we know that in data warehouse there is something useful for us, but give us more specific information. And
so they have to come to you and ask you for something.
Exactly, that because they don't know about what exactly is in data warehouse.
So that's what this think tank tries to promote, the idea that you can go ahead and get it yourself and start building a project around it without having to wait for somebody else to give you access to the data or to give you the data in the format that you want.
But then I would call it self-service BI.
And
in this
it's
case,
not just BI, because you use it for data data science. It's not BI. BI is just something else. But again, I'm not agreeing. Yeah. I'm not.
I'm just trying to observe because it's actually spreading out, and you don't know what to do with that. So.
Yeah. So yeah, I absolutely agree.
If I recall this correctly, for data lake, you really say collect actually everything, yeah, and not just for data mart is mostly domain specific for some department, and it's much more clean data. So for data lake, you really say putting external data sources inside, and then having some analytic data scientists or data analysts who are trying to combine this different data and getting new insights.
But without preparation of data, with unstructured data, anyone from a department who cannot work with such kind of type of data, they definitely will come to IT and will say, guys, we know that in this system there is something interesting for us, bring that to data warehouse and
But
so
if they have the capabilities, I mean, they have like a smart guy that knows a bit of data science, why
then that smart guy does wrong job. Also, that smart guy must be by IT department,
not
not by.
necessarily. Why? Because in order to do data science, and correct me if I'm wrong, proper data science, you have to understand the business a lot more than you do in IT. I mean, for my example with the carriers, you know who has the most information about what happens and that actually can tell you if the data is correct or not, are the guys on the field, the guys working with the carrier. So it's a department-specific knowledge that you have to have. So in order to create something that makes sense for a particular business unit or for a particular project, you want to be there, you want to be in the trenches with the guys in order to solve the problems, right? So data science, at least from what I can tell, should not be an IT only function. It's a function that depends on the problem that you're trying to solve, and the closer you get this IT guy, called the data scientist, to the actual business problem that he has to solve, rather, of course, you can move it around if it's the case, but in general, having it closer to where the problem resides could solve a lot more issues, because he knows what type of sensors he could bring in, right, that are not available now. Let's think about like a retail store, right? If there's a data scientist that can look at the type of information that's on the checks, on the tickets, like on the invoices of every customer, he can think about a way of correlating, a sensor that tells, oh, by the way, I've seen a sensor, very interesting sensor, that looks at, identifies customers by their height. So you have this camera. Of course, you can't track a guy and just have a record of who entered and who bought and what he did, because it's personal identifiable information. You want to try to avoid that. So what they do, they measure the height of the person, because apparently it's kind of a unique way of identifying a guy around. So they track what he does within a store, where he goes, what does he do, and eventually what did he buy. And then we can do a kind of a correlation back. So this kind of information is not in IT. Right? The IT doesn't know what happens in the shop. This is an information that, as a model, as a behavior of business that resides in the business unit, but the business unit does not know what's possible or what could be extracted. Right? So this is what I'm trying to promote, is the idea that you have the data service that could be used as a correlation for all these guys that should be spread, not necessarily concentrated within IT. And maybe this layering of IT and business and marketing is not necessarily a good thing either. A lot of companies are spread out in individual groups, and more companies within companies and within companies, because they've seen that if we have distributed systems, why shouldn't we have distributed companies? I mean, why build like a huge monolith in terms of companies? Why have the layering? It's the same type of reasoning applies in this field, right? So I don't know, but again, these are my opinions and my ramblings. I'm not necessarily correct.
Question, maybe as an old question, do you propose this architecture for operative systems, like business systems that are working on just for data analytics?
So microservices in general. Microservices in general, I think, are very useful for operational systems because they're highly available, highly scalable, and they can solve a lot of headaches. Because, for instance, it's a lot easier to create a Docker image than to provision a whole bunch of machines using Puppet or Chef. So in my experience, it's easier. It solves a few issues, but of course, granted, it introduces other issues. So it's not a global panacea that is going to solve everything. And unless you have a proper application design, which like 90% of the applications don't have, it's hard to implement. So you don't want to go microservices all the way, regardless of what you do. It has to make sense. But assuming it makes sense, and assuming you can disconnect components from each other, and you can introduce some asynchronicity between the components, I think you really can get a lot of, from an operational perspective, a lot of resilience and a lot of peace of mind and performance out of this, because you can have a higher granularity. You can scale each component individually, right? And people can release independently. Then you don't have to have this hugely planned rollout of the entire machinery, right? Whenever you do a release, you just release a little component. If it breaks, we roll back. can just roll back that particular component. It's not that bad. And, you know, Netflix has a Simian army thing, when they like kind of destroy services to make sure that things work continuously. They randomly destroy services in their architecture. But again, I'm not saying this applies to everything. So I'm just, the basis of this talk is that I'm giving you the ideas, but you kind of have to make decisions on your own.
What about redundancies?
Sorry.
What about redundancies?
Redundancies?
Within microservices, yes.
Well, by default, microservices are redundant, right? So every individual component has multiple instances of itself, right? So my shopping cart has 10, 20 components, 10, 20 instances of the shopping cart. You do load balancing on them, right? And then there's another component that does load balancing in itself, like the backend processing services. So the redundancy is built into microservices by default, by design.
Is there a way to impose this architecture on, let's say, legacy systems? I have a bunch of JE systems. Does it work?
Bunch of
JE systems, like you do have application service that should run in a small Docker container.
JE, yeah. Well, you can if you want to, and it's absolutely okay. Problem is state. Where do you keep the state of those services? Usually when somebody designed the J2EE application with dependency injection and all the required things, it gets pretty big and pretty intense in terms of resource utilization and also dependencies. But now I'm not talking about dependencies in terms of other jars or components that it uses, but rather other services that it has to talk to. Because if it's big, as a set of responsibilities, it will also talk to a lot of other services. And so it gets really complicated to make that thing, to roll it out, because it would connect to a whole bunch of other stuff. And I think it's going to be harder to make state move outside. So the microservices promote the idea that the state is residing in a database. When I say state, I say something like session. Right? The session usually has to stay somewhere else if you want to load balance across a multitude of application servers. And so state for a J2EE application can mean a lot of things. Right? It could be locking that you need to make things work between the processes. Right? Maybe an application spawns multiple processes, you have to do locking. So I don't know, it depends. Some applications might be easier to port, some applications might not. So I don't know. The answer is I have no idea. It depends.
Do you have, could you talk some assumptions on usage of Mesos and Marathon versus an example Kubernetes?
Kubernetes has been, so Mesos is definitely less used than Kubernetes. Mesos is just been coming around, but it's really catching up because the Mesosphere company, which has built Mesos is an open source project, and Mesosphere commercializes it as a data center operating system. It really gains a lot of traction. So I think we're going to see more Mesosphere than Kubernetes in a while, simply because of the quality of the software. Because they only do this, and they've created this, nice UI on top. That's David, you wanted to say something? By the way, you have to talk. In like 1 minute.
Just a question regarding service-oriented architectures.
Okay, did you got over? Sit there downstairs?
No, you have 5 minutes.
Okay, so we're gonna leave in about 2. Sorry.
Yeah, just a question regarding service-oriented architecture. I mean, IT reinvents itself from time to time, right? So years ago we had something like SOA there, and it started all by having several services that were talking to each other, which sounds a little bit like the Microservices idea anyway. But what they did was actually they just put it like enterprise service buses or integrate the service landscape in a way. How is this looking for microservices? Are microservices following the SOA approaches at the end, or
I think they are
more or less the independent, decoupled stuff like that?
So the concept is the same. I mean, the problem of decoupling components has always been around. So everybody that has been doing programming knows that you have to decouple components to make it properly work. So the problem is the solution to that. I think there are different solutions to the same problem. And properly designing dependency injection in a J2EE application is one solution. And microservices are another solution. I don't know if you've been around when Corba was around, but that was a huge, huge problem. But again, it was a solution to scaling out services. Different solutions. I think that with this new, more agile way of describing things like JSON, you get a lot more flexibility. So I think it's about flexibility in terms of component interrelation. I think this is like the lossless state in which we could have gotten into as opposed to what we have until now. So we really managed to decouple components. Now we have REST services, which are by far the easiest things that you can implement, and JSON, which is a lot more extensible and looks a lot better than XML. So there have been like evolution stages.
But you still see something like ASPs in this microservices landscape.
So I think conceptually they're the same, right? Yeah, different solutions. Yeah, please. Last question. But you can keep continuing discussion. I mean, I just have to leave.
So with this model specifically, I mean, you put the emphasis on it being stateless and all these sorts of things. So how would you deal with, in this particular case, situations where you have to track not only the data lineage, but also the persistence of metadata across the life cycle of the data management?
So
if you need to archive it for audit purposes. And
so I haven't talked about this, but usually microservices can't exist without synchronization technologies, right? So synchronization is, instead of being done, what do you do at the operating system level when you have synchronization? You use something like a mutex, right? And within a single operating system, these are the services that the operating system provides. Mutexes, shared memory spaces, process management, right, resource management. The microservices view an operating system, if you like, across multiple hosts. So the operating system becomes a collection of, a resource manager, which is the Mesos, a synchronization or mutex system, which could be Zookeeper. Right? Zookeeper guarantees you that you have a single system image, right? You see the same thing dependently on where you're looking at it, but it's distributed. And you can use it as a distributed log. So you have your mutex-like structure. And you also have queues that you used to have in the operating system with Kafka. So and absolutely, you can't have applications that do not talk to each other, that are not synchronized with each other. So there are many situations where you want to block something and you want to make sure that it's a single guy talking to it. And these are the synchronization services. I haven't got into them, but they're and I think we'll see a lot of alternatives popping up here and there to Zookeeper and to and Kafka, of course, is like the fifth queuing system in existence. Did I answer your question?
A little bit, but we'll discuss it more offline.
So unfortunately, I have to go. But maybe you wanna have a short break, and then David, if you like, you can continue.
Basically, we did an introduction to Couchbase. So if you don't know Couchbase yet, then hopefully you can do that.
Thank you, guys.